I'm going to talk about section 7.3, which is a polar form of complex numbers. We talked about polar equations before, and now we're going to talk about the polar representation of just the complex numbers. So in 7.2, we talked about that we could graph a complex number using a vector. So we end at the terminal point a plus bi, and we said it had a modulus, which is the length of the vector, the magnitude of the vector, which was r, and an argument, which is the direction of it, which is theta. And we remember that we used our a and b, our real part and our imaginary part, to calculate the modulus and to calculate the argument. And this is what we came up with. Now we're also going to use this for polar form. Remember, for regular form of our complex numbers, we have a real part and an imaginary part. Just like with real numbers and rectangular coordinates, and we had x and y, and then we switched to r and theta for polar form, that's what we're going to do for complex numbers. We're going to go from our real and imaginary parts to our modulus and argument, our r and theta, being the new polar form. So we know how to go from a and b, from our regular complex form, to our polar coordinates r and theta. But what happens if we have r and theta and we want to go to our regular form? Well, we use the same idea we did when we came up with polar form before. We know that r is equal to, we use cosine and sine. Cosine and theta is adjacent over hypotenuse, and sine is opposite over hypotenuse. So we end up that a is r times the cosine of theta, because cosine is adjacent over hypotenuse, so we multiply that hypotenuse up there. And our b is r sine theta, which is just like we had before. Now, the notation is a little bit different from when we did rectangular form to polar form. With complex numbers, if we replace this, we have r of cosine theta plus r of sine theta times I. So our real part is r cosine theta, and our imaginary part is r sine theta. And the way we write this, we can factor out an r here. And this notation is oftentimes shortened to just this, r cis theta. What this means is cosine theta plus I sine theta. That's this right here. It's just a notation thing so that you don't have to write out this whole cosine theta plus I sine theta every time. So let's look at some examples. If we have this complex number, negative 4 minus 3i, and we want to change it to polar form, well, the first thing we want to do is kind of figure out where it is. Well, negative 4 and negative 3, so it's down here in this third quadrant. So we want to keep that in mind so that when we find our argument, we make sure we've got the right one. So we know that r is the square root of the real part squared plus the imaginary part squared. And so we've got 16 plus 9, which is 25. Take the square root and you get 5. And our argument, theta, is the inverse tangent of negative 3, the imaginary part, over the real part, negative 4. Now, your calculator is going to give you an answer up here in this first quadrant, because it's going to end up negative divided by negative, it's going to be positive. So it's going to give you one in this first quadrant here. So you're going to have to add pi to it, and you're going to get 3.785 radians for your argument. Make sure you get that right. So the way we would write this is negative 4 minus 3i equals r times cis of theta, which is the same thing as r cosine of theta plus r sine theta, and then I. So this is the shorthand notation for this. But this is the regular complex form, and this is the polar complex form. Now, what if we have a polar form and we want to go to our regular rectangular complex form? So we know that A is r times the cosine of theta, and B is r times the sine of theta. So A is 16 because this is r cis theta. So we have 16 times the cosine of 7 pi over 4. You know from your unit circle that the cosine of 7 pi over 4 is the square root of 2 over 2. So we have 8 times the square root of 2. And here we have the sine. We know from our unit circle that the sine of that is negative square root of 2 over 2. So we have negative 8. So we have our real part, and then our imaginary part times I. So here's the rectangular form from this polar form. Now, we want to check this and make sure we have our signs all right. 7 pi over 4 is down here, which means our real part should be positive and our imaginary part should be negative, which is what we ended up with, so we're good. Now, on pages 360 to 361, they show you how to get some formulas for multiplication and division of polar form. I'm not going to go through that with you because it's very well done in the book, and I want you to read it step by step and make sure you know how to do that. But basically what you have is this multiplication. If you have one imaginary number in polar form and you multiply it times another imaginary number in polar form, then you end up with, you multiply the two r's together and then add the two arguments. This is because of all our formulas we learned, our sum and difference formulas from sine and cosine, things like that. So make sure that you look at that proof where they show you how to derive that formula. And then for division, it's a very similar thing. If you have two complex numbers and you're dividing them, then you divide the r's and subtract the arguments, the thetas. So for these formulas, make sure you've read these pages and understand how they got them. So for an example, let's look at if we have 12 cis 5 pi over 3, so that's one complex number, and 4 cis 2 pi over 3, that's another complex number. Then we want to multiply those two. We multiply our r's. 12 times 4 is 48. And then we add our arguments. So we have 7 pi over 3. Now, 7 pi over 3 isn't on the unit circle. We go around and we have, that's 6 pi over 3, 7 pi over 3. We're up here. So what we need to do is change this so that it's between 0 and 2 pi. And it's pi over 3 because we went around the unit circle once and then pi over 3 more. So there's our answer. We multiplied these two together, and this is the complex number we got. Now if we want to divide them, we divide our r's. 12 divided by 4 is 3. And then we subtract our theta. So we have 5 pi over 3 minus 2 pi over 3, which is just 3 pi over 3, which is just pi. So when you divide these two, this is what we get. So make sure you've looked over this page as well as the rest of the section so that you understand how we get these formulas. They're very easy to memorize. I expect you to memorize them because they take almost nothing to deal with. So make sure you know these and know how to use them, and we'll talk about this some more in class.